Today we are going up to some really big numbers. Here we go. Let's start with a trillion. A trillion is pretty hard to comprehend. For example, a trillion seconds is around 32,000 years, but it is nothing compared to the numbers we're going to get to soon. Let's keep going up. Next we have a googol, which is 1 followed by 100 zeros. To understand how big this is, there are 10 to the 86 particles in the universe. That's 1 followed by 86 zeros. So a googol is significantly larger than this. We have now reached googolplex, which is 1 followed by googol zeros, or 10 to the 10 to the 100. To grasp how big this is, think about this. An average human takes up 1 meter cubed of space. In 1 meter cubed, there is 10 to the 10 to the 70 ways of particles arranging themselves. This means that in this space, particles could arrange themselves into a penguin, a cat, a clock, a worm, and much more. The number of different arrangements is still less than googolplex, meaning that if the universe contained a googolplex meters cubed, then it is inevitable that there would be repetitions of particle arrangements, meaning that there would be another U. Now we move on to Graham's number. To understand how we created Graham's number, imagine a square with all its vertices connected by lines which are colored either green or red. Now imagine a cube with all its vertices connected by red and green lines. Finally, imagine a 4D cube with all its vertices connected by red and green lines. How many dimensions do you think we could go up to before our cube has at least one side in which all the lines connecting the vertices are the same color? Well, it turns out the answer to this question is between 13 and Graham's number. But how big is Graham's number? In order to get somewhat of an idea of how big this number is, we must use a notation known as arrow notation. In arrow notation, 3 up arrow 3 means 3 times 3 times 3, or 3 to the power of 3. 3 double up arrow 3 can be rewritten as 3 threes with 1 up arrow between each 3. Here I've used brackets around the last pair of 3's to make our next calculation easier. We know 3 up arrow 3 equals 3 to the 3, so we can substitute this in. 3 up arrow 3 to the power of 3 is the same as 3 up arrow 27, which is equal to 3 to the power of 27, or approximately 7 trillion. Now let's look at 3 triple up arrow 3. This means 3 threes with 2 up arrows between each 3. Once again, I've used brackets to make our next calculation easier. We just calculated 3 double up arrow 3 to be 3 to the 27, so we can substitute this in. We then know 3 double up arrow 3 to the 27 is equal to 3 to the 3 to the 3 continued until we have 3 to the 27 threes in our power tower of threes. This number contains 3.6 trillion digits. Finally, let's analyze 3 quadruple up arrow 3. This is the same as 3 threes with 3 up arrows between each 3. We know 3 triple up arrow 3 is equal to the 3.6 trillion digit number that we calculated earlier. So now we have 3 triple up arrow and then our 3.6 trillion digit number. In order to understand what this means, imagine our huge 3.6 trillion digit number, then imagine writing a 3 for every number up to this huge number, while placing 2 up arrows between each 3 that you write. Now that we have this image in our head, we're going to try and get rid of some of the up arrows. We know 3 double up arrow 3 equals 3 to the 27, so we can substitute this in. We then know 3 double up arrow 3 to the 27 is equal to 3 to the 3 to the 3 continued until we have 3 to the 27 threes in our power tower of threes. The number that results from this would become the number of threes for our next power tower, and then that number would become the number of threes for our next power tower, and so on. You remember that 3.6 trillion digit number that we derived earlier? Well, for each number up to this huge number, we repeat this process, and only then do we reach the result for 3 quadruple arrow 3. This number is huge, but we are not even close to Graham's number yet. The result that we derive for 3 quadruple up arrow 3 becomes the new number of arrows that we put between our two threes. The result of this expression then becomes the new number of arrows that we use in our next expression. And then the result of that expression then becomes the new number of arrows for our next expression. This happens 64 times, and then, and only then, do we finally reach Graham's number. Now we skyrocket up to tree 3. In order to understand the number tree 3, we must play a bit of a game. In our game, we're going to create a forest out of seeds that look like these. In our tree 1 game, we will only use one color of seed. In our tree 2 game, we'll use 2 different colors of seed. In our tree 3 game, we'll use 3 different colors of seed, and so on. The first tree in our forest must contain at least 1 seed. The second tree must contain at least 2 seeds. The third tree must contain at least 3 seeds, and so on. If an earlier tree can be contained in a newly created tree, then the forest dies. This includes instances where 2 or more seeds have the same common ancestor in 2 trees in the forest. For our tree 1 game, the forest dies after the first tree is created, as once you have placed 1 green seed, you can't produce any more trees without having a green seed contained in it, which would break our second rule. For our tree 2 game, the highest score we can get is 3, as any trees after these 3 would either contain a green seed, 2 blue seeds that are connected, or 1 blue seed. For our tree 3 game, we see our numbers of trees skyrocket. In fact, the number of trees we can create in this forest makes Graham's number look like it's 0 in comparison. I have drawn 8 trees, but there is much, much more. That was Big Numbers with Jazz Learn. Hope you learned something new. Leave a comment if you want to go even higher.